Hi, this is lecture 5 of our course, Introduction to Complex and Algebraic Geometry. Today we are going to discuss the notion of higher dimensions. So this is essential for complex and algebraic geometry. But before really diving into complex geometry in higher dimensions, we are going to discuss what we really mean by dimension. So think about the real numbers, R. We think about R as a one-dimensional space. The set of real numbers, we think about it as a straight line, right? There's 0, 1, 2, etc. And from the other side, -1, -2. This line, it's a line without any thickness. So this is essentially one-dimensional. So it's a one-dimensional object. We think about any curve, say something like this, also as a one-dimensional object. So if I pick any point on this curve, let's say a point X, if we think about a small neighborhood of X, so points which are very close to X, let's say like this, just a neighborhood of X, it really looks like neighborhood of any point in R, right? So this red interval is really like an interval inside R. This means this space locally looks like R, right? And therefore we call it also one-dimensional. Also think about a circle, the boundary of a disk. So just the boundary, the circle itself, not the thing, not the two-dimensional disk itself, but just the boundary. The boundary is also one-dimensional. If I pick any point X on the circle, the small neighborhood of that point, again, looks like an interval inside R. So we call this a one-dimensional object, right? So these are one-dimensional real objects. What do we mean by two-dimensional objects? So if we think about R2, the plane, XY plane, the whole plane, we think about this as a two-dimensional object. So let's say if you think about surface of the Earth or surface of a ball, suppose it's empty, suppose there's nothing inside, the surface is a two-dimensional object. If I pick any point X on the surface of this object, any small neighborhood of that looks like a small neighborhood of any point inside R2, right? These two things are very similar. So surface of a ball is a two-dimensional space. Or just as another example, suppose we have a torus, which looks like the surface of a donut. Again, the surface of this object is a two-dimensional object. If I pick a point X here, a small neighborhood of that kind of looks like a small neighborhood inside R2. So these are examples of two-dimensional surfaces. I would be thinking about three-dimensional objects. R3 is an example of a three-dimensional object, right? We have X, Y, Z. We need three numbers to describe coordinates of a point. This is a three-dimensional object. It's hard to think about other three-dimensional objects. So when we were thinking about surface of the Earth, which is a two-dimensional object, we think about it as something embedded inside three-dimensional space, right? So here our two-dimensional object is living in this picture inside R3. So if I want to think about other three-dimensional objects, I probably need to think about them as being embedded inside some higher dimensional space. However, we can't really imagine that. That's why other three-dimensional objects are quite hard and complicated to think about. So, but they exist mathematically. They exist. They might even exist as a physical reality. And then after the things become even harder, we can't even imagine R4, right? It's not easy to imagine that. However, both mathematically and also maybe in the physical sense, it makes sense to think about any dimension, Rn, for any natural number. So I think about Rn as R times Rn times, which essentially means any point here can be described with n real numbers. So any point in Rn can be described with n couple of numbers, x1 up to xn, where each of them, x1, x2, x3 up to xn, is a real number. Okay, so this is our Euclidean n-dimensional space. And these are real n-dimensional objects. Now, there is a complex version of the same story. So when we think about R, R2, R3, Rn, and etc., and we call them one-dimensional, two-dimensional, three-dimensional, n-dimensional, we mean dimension as a real space. So we say dimension of Rn as a real space is n. Now, there is a complex version of the same story. So what do I mean by complex version? So in this course, we are mainly thinking about functions on C, right? C is essentially, as we've seen before, the same as R2, right? And R2 is two-dimensional. It's two-dimensional. It's a two-dimensional real space. But we also kind of like to think about C as a complex object. And as a complex object, C is just C to 1. So we kind of think about it as a one-dimensional complex space. So if you ask me what is dimension of C, I would say as a complex space, it's one-dimensional. As a real space, it's two-dimensional. Now, just like higher dimensional real vector spaces, we can think about the higher dimensional complex vector spaces. We had R, R2, R3, etc. Now we have C, we can think about C2, right? C3, etc. So what is C2? Is essentially C times C, right? And well, C itself is R2, so it's R2 times R2, which is just R4, right? So C2 is essentially the same as R4. R4 is a four-dimensional real vector space, but now C2 can be understood as a two-dimensional complex vector space, right? And we can do this in any dimension. We can think about C to the n for any natural number n, which is C times C n times, right? Now, each C is a copy of R2, so we have R2 times R2 n times, which is R to the 2n, right? So Cn is just by definition the set of numbers of the form Z1, Z2 up to Zn, where each Zi from Z1 up to Zn is a complex number, right? Now, Z1 is a complex number, so I can write it as some real number, say x1 plus I, another x number, say y1. Up to Zn is a complex number, so it can be written as a real number plus I, another real number. Let's denote them with xn and yn. Okay, so here in this identification, the point in R2n that corresponds to Z1 up to Zn is essentially x1, y1, x2, y2, etc., up to xn, yn, right? There are 2n real numbers, so it's an element of R2n. So we kind of identify this point with z1 up to zn, right? That shows Cn is essentially R2 to n. So this is 2n dimensional as a real space, but it's n dimensional as a complex space. Okay. Now, what's the point of this? So just like in calculus, we started studying functions from R to R, but very soon you would get to study functions which are the domain and target are not one-dimensional, but they're higher dimensional. You get to study functions from, say, Rn to Rm, right? Say, you would study functions from R2 to R3 or things like that. Same thing happens here. So we started with the study of functions, mainly holomorphic functions from C to C. Now it's natural to extend our discussions to function from Cn to some Cm, so in higher dimensions. So there are different reasons one might want to study higher dimensional spaces. These higher dimensions are not necessarily real higher dimensional spaces. When you study math or even engineering, a lot of times there are a lot of parameters and they naturally appear as higher dimensions. Also in math, in a lot of problems in geometry, topology, PDE, number theory, etc., higher dimensions appear naturally. Well, also in physics, there might be that there are higher dimensions. I mean, I'm not a physicist, but in some models of the real world, say, for instance, in string theory, people tend to think about the world in some models as 10-dimensional, where these 10 dimensions appear as the standard four-dimensional space, which we can see, three dimensions that we can observe, plus time, plus extra six dimensions which we cannot see. And those extra six dimensions are extra six real dimensions or three complex dimensions. So these extra dimensions we can't see are somewhat locally, they're supposed to look like C3. So these also appear in some models of physics. I'm a mathematician, so I'm not the best person to say if these models are realistic or not. But anyways, in a lot of problems in math and physics, these higher dimensions appear. So previously we discussed when we would say a function from C to C is holomorphic, right? So in the next lecture, we are going to discuss what does it mean for a function in higher dimensions to be holomorphic. That would be our discussion for the next session of lecture 5.